Good morning and welcome to the fourth video lesson in the module Laplace transform. Today we are going to discuss Laplace transform, some special forms or special functions. The main agenda are we simply revisit the results we have learned in the previous classes. Laplace transform of product with t, the Laplace transform of division by t, inverse Laplace transform, and we will discuss some problems from all these sections. So first of all, we are going to revisit the basic results that we have learned. What are the Laplace transform of a constant function, Laplace transform of 1, Laplace transform of basic trigonometric functions like Sine A T, Cos A T, and exponential functions, and main properties of Laplace transform, etc. Then Laplace transform of derivative is actually the product with s. That is a wonderful result that we have learned in the last session. In the time domain, the derivative is transformed into a multiplication by s in transformed domain or s-plane. And similar result is Laplace transform of integral is division by s, or in other words, in time domain, integration is transformed into division by s in transformed domain, or Laplace transform transforms integration into division by s. The most important results that we have discussed in the first two sessions are Laplace transform of 1 is 1 by s. Laplace transform of e raised to at is simply shifting 1 by s minus a, shifting of this 1 by s by a units. Laplace transform of sin at is equal to this a by s square plus a square. Laplace transform of cos at is s by s square plus a square. Laplace transform of sin h at equal to a by s square minus a square. In case of sin at, it is a by s square plus a square. Similarly, Laplace transform of cos h at is equal to s by s square minus a square. Laplace transform of t raised to n is equal to n factorial by s raised to n plus 1. In this case, we assume n is a positive integer. Otherwise, we will use generalized form of factorial, that is gamma function, gamma of n gamma of n. E raised to at is into f of t. That is, we multiply f of t by e raised to at, then take the Laplace transform, we got f bar of s minus a. That means we simply replace s by s minus a in f bar of s, the transform of f of t. Now we are going to discuss what happened when we take transform of a function after multiplying by t or power of t. So this is a wonderful result. Laplace transform of a product with t is equal to minus d by ds of f bar of s. In the previous lesson, we know that Laplace transform derivative into multiplication by s, derivative into multiplication by s. Now multiplication by t is transformed into derivative. There is a connection between these two operations. Laplace transform of product with t is derivative of this f bar of s. We can extend this result to a power t raised to n. So Laplace transform 1 multiplication by a single t gives 1 derivative with a negative sign. So Laplace transform of t square and f of t gives minus 1 square d square f bar of s by ds square, and we can extend it into n power. So the result is Laplace transform of t raised to n f of t is equal to minus 1 raised to this n into nth derivative of f bar of s. So Laplace transform of a product with t is transformed into derivative of f bar of s. First problem, Laplace transform of t sine omega t. So here sine omega t is a very simple basic trigonometric function. We know its transform. Laplace transform sine omega t is equal to this omega by s square plus omega square. Then what happened when this function is multiplied by t and then take Laplace transform? Now we know we simply calculate transform of sine omega t and take derivative and multiply by negative 1. So given function is a product with t, so we apply the theorem. Laplace transform of t into f of t is equal to minus d by ds of f bar of s. There is an easy method to write this formula. First of all, you just hide this t by our hand or a single finger. Then the remaining portion is L of f of t. We hide this t, then read the left side, that is L of f of t. That is here, L of f of t. More clearly, to find L of t sin omega t, you just understand that this is multiplication by t, then hide t. That is L of sin omega t. We know multiplication by t results in derivative minus d by ds. Then hide, that is the effect of multiplication by t. Now hide this t. That means the effect of t is here, minus d by ds. The remaining portion is L of sin omega t. L of sin omega t. Write that. Now calculate this one. L of sin omega t is omega by s square plus omega square. Then we have to take the derivative. See, numerator there is no s term. We are going to take derivative with respect to s. So this omega can be taken outside. Then the remaining portion is 1 by x, like 1 by x. Derivative of 1 by x is minus 1 by x square. We use that. So I take this omega outside. Then minus 1 divided by s square plus omega square whole square. And also into derivative of this expression, this argument. Derivative of this argument with respect to s is 2s. Now on simplification, this minus and minus get positive. Then numerator becomes 2s omega or 2 omega s. So final answer is L of t sin omega t is 2 omega s by s square plus omega square the whole square. L of t sin omega t equal to 2 omega s by s square plus omega square whole square. Naturally, next function is Laplace transform of t cos omega t. Here also we have a product with t. First of all, we find Laplace transform of cos omega t, then take the negative derivative of this. We start with the theorem L of t f of t is equal to minus d by ds of this f of transform of f of t. We hide this t, L of f of t, that is f bar of s. So we substitute the function here instead of f of t cos omega t. Now we will understand like this. It is a product with the t. So t raised to 1. So minus d by ds is there. When we put minus d by ds on the right side, the t is eliminated from the scene. The remaining portion is L of cos omega t. Write that here. Now calculate this. L of cos omega t is s by s square plus omega square. But the difference is here both the numerator and denominator contains s terms. So we have to take quotient rule. Denominator into s square plus omega square into derivative of the numerator, that is 1, minus numerator s into derivative of the denominator, that is 2s. The whole divided by denominator square, s square plus omega square the whole square. When we simplify this expression, we got a negative term 2s square. Here a positive s square. So we got minus 2 s square plus s square, that is minus s square. There is a negative outside. Taking all these together, we got minus s square plus omega square the whole minus divided by s square plus omega square the whole square. Multiply by that negative to the inside portion, we got s square minus omega square by s square plus omega square the whole square. We cannot cancel these terms. This is s square minus omega square. This is s square plus omega square the whole square. Next is Laplace transform of division by t. We know multiplication by t leads to derivative. So division by t automatically leads to integration. That is this theorem. This theorem states that Laplace transform f of t is equal to f bar of s, then L of f of t by t is equal to division by t. The effect of this t is integral. Integral is to infinity, then L of this numerator, that is f bar of s ds. So division by a single power t gives one integral. So by t square gives double integral. So we can extend this result to any power. There is a next result. We can generalize the theorem to t raised to n, that is L of f of t by t raised to n is equal to n times integral, limit from s to infinity f bar of s. Because there are n integral, we should have n ds. The first problem, find Laplace transform of sin t by t. From the first look, we know that this function is divided by t. So division by t. By this theorem, division by t leads to integration. So L of f of t by t is equal to integral s to infinity L of f of t ds. Next step is, instead of this f of t, we would sine t. So L of sine t by t is equal to, this division by t leads to this integral. So we can hide this with your finger. Remaining portion is L of sine t. We write like this. Now calculate L of sine t. L of sine t is equal to, here the coefficient of t is 1. So 1 by s square plus 1 ds. And we know that integral 1 by 1 plus x square is tan inverse x. Use that result. So tan inverse s, but the limit varies from s to infinity. Now put upper limit infinity. Tan inverse infinity minus tan inverse s. Now think, to what angle we get tan value infinity? Tan is actually sine by cos. Sine by cos becomes infinity when cos is 0. Cos is 0 when theta is equal to pi by 2. So tan inverse infinity is pi by 2 minus tan inverse s. Pi by 2 minus tan inverse s leads to the complement of tan, that is cot inverse s. So we start from L of sine t by t. So we just hide t. So division by t leads to integration. Then write L of sine t here. Evaluate L of sine t. Evaluate this integral. Substitute the limit and write the complement function of tan inverse due to the presence of this pi by 2. So we got cot inverse s. Another problem. Again this problem contains division by t. Division by t leads to integration. So we just hide this t. The effect of by t is integral s to infinity L of this numerator. That's all. We'll do that. We state it. Argument involves t in denominator. So we use this theorem. We hide this t. Effect of the t is integral s to infinity. The remaining portion L of cos 2t minus cos 3t. Laplace transform is linear, so L of cos 2t minus L of cos 3t. L of cos 2t is s by s square plus 4. L of cos 3t is s by s square plus 9. Substitute that. L of cos 2t, L of cos 3t. Now we are going to integrate this, and we simply recollect this form. S square plus 4, its derivative is 2s. If you got 2s in the numerator, we can say that the du by u form. Integral du by u is log u or ln of u. To make it 2s, we simply take 1 by 2 outside and put 2 here and here. So 2s by s square plus 4 minus 2s by s square plus 9. I take 1 by 2 common. Numerator is derivative of the denominator, or du by u. Integral du by u is ln of u, ln of s square plus 4 minus this is ln of s square plus 9. Limit varies from s to infinity. The next step is log a minus log b. Log a minus log b is logarithm of a by b. Now remember, when we put upper limit, this numerator becomes infinity, denominator becomes infinity. That means it is of the form infinity by infinity. We can think it in another way. Numerator tends to infinity and denominator also tends to infinity or the same rate, because numerator is s square, denominator is s square. So the order of convergence to infinity in numerator and order of convergence to infinity in the denominator are same. So numerator and denominator are same. So it becomes 1. An x by x like that. X by x automatically tends to 1. Then logarithm of 1 is 0. So when we put upper limit, we got 0. Minus when we put lower limit, we got the same expression. That is half into 0 minus logarithm of s square plus 4 by s square plus 9. Minus of log is logarithm of 1 by. So it reciprocal will become in the inside portion. We will do it in algebraically. I take s square from the numerator inside this bracket and s square from the denominator inside this bracket. So s square and s square get cancelled inside this bracket. So this time becomes 1, this time becomes 4 by s square. Similarly 1 plus 9 by s square. Now we put infinity to this numerator and denominator. Now infinity is in the denominator. So 4 by infinity, 4 by a large quantity tends to 0. So numerator becomes 1 plus 0 or 1. In the similar argument, denominator also tends to 1, as we said in the previous case. So logarithm of 1 by 1, log 1 is 0. That is next step. When we put the lower limit, we got the same thing. There is no change. Then we simply take the cross multiplied form. So s square plus 4 by s square divided by s square plus 9 by s square. So s square plus 4 by s square plus 9. Now we put log 1 is equal to 0. Log 1 is equal to, when log 1 is equal to 0, we got minus of logarithm. Minus of logarithm is logarithm of 1 by. So we got the reciprocal of the argument. Half ln of s square plus 9 by s square plus 4. One more step, we can take this 1 by 2 inside, because a log b is equal to logarithm of b raised to a. So logarithm of s square plus 9 by s square plus 9 the whole raised to half. That is square root, logarithm of square root of s square plus 9 by s square plus 4. This much step is sufficient. Now we think about a more higher problem. Find the Laplace transform of square of sine 2t by root t. First of all, we calculate the square. So numerator square by denominator square. Sine square 2t by root t square or t. Sine square 2t by t. So the expression becomes 1 minus cos 4t by t. Again division by t. Division by t leads to integration. So we use the Laplace transform formula. L of sine 2t by root t the whole square equal to L of the simplified expression 1 minus cos 4t by 2t. I can take this 1 by 2 outside. Then the t in the denominator. Division by t is integral. So integral is to infinity. Then hide this t. 2 is outside. So no denominator now. Then remaining portion is L of numerator, L of 1 minus cos 4t. Now evaluate this L of 1 minus cos 4t using our linearity property. That is L of 1 minus L of cos 4t. L of 1 is 1 by s minus L of cos 4t is s by s square plus this 4 square or s by s square plus 16. Now we will integrate this. This portion is ln, but this portion cannot be now ln, but this integral become ln by put some 2s here. So 1 by 2 into 2s by s square plus 16. It's a mathematical manipulation. Now the derivative of this s square plus 16 is 2s. So du by u form, integral of du by is ln. Here also we have ln of s. So ln of s minus half times ln of s square plus 16 s to infinity. Remember, before substituting the limit, we have to put in the single log. So this 1 by 2 should be come into the inside portion. So half log x is equal to ln of x raised to half or ln of root x. Use that result. Minus is there. Then half going to the inside expression. So ln of root of s square plus 16. Now log a minus log b. So we can write it as log a by b. So logarithm of s divided by root of s square plus 16. Now in such cases, logarithm of some a by b, and the numerator power is s raised to 1. The denominator there is a square root. So square root of s square also leads to s. So order of convergence to infinity is again same. In that case, we simply reciprocal this inside expression. That is ln of root of s square plus 16 by s. Otherwise you take s from the numerator. Here the highest term is s square, but when we take it outside the root, that becomes s. S and s get cancelled like that. We got the same thing. The lower limit is itself. So half into ln of root of s square plus 16. I put it everything in single root. So root of, here actually square root is only for numerator. When I put it in the denominator, we have to take square of the denominator. So square root of s square plus 16 by s square. Then logarithm of root is equal to half log. So we can take half from this inside portion. So we got half into half, that is 1 by 4 ln of s square plus 16 by s square. So division by t. Division by t leads to integration. Another problem, it contains many expressions. The outer expression is e raised to minus 3t. It leads to scaling in Laplace. Then integration. Then Laplace transform of integral becomes division by s. Then division by t. That leads to integration. We have to put it all together. So we start like this. We need Laplace transform. So in mathematical expression, L of this question is L of e raised to minus 3t integral 0 to t sin t by t dt is equal to. Now we look like this. The outermost operation is e raised to minus 3t. In Laplace transform domain, multiplication by e raised to minus 3t leads to a scaling. So s tends to s minus a, that is s tends to s minus minus 3s plus 3. That is I put like this. You should put a bracket, that is outside operation, last operation, that is s tends to s plus 3. So e raised to minus 3 effect is like this. Next operation is integration. Laplace transform of integral is simply division by s or 1 by s. So I put 1 by s. So this much operation is over. Next is division by t. Division by t is integral s to infinity. So instead of this division by t, I put integral s to infinity in transform domain. The remaining portion is only sine t. It's Laplace transform. So L of sine t. Now we calculate L of sine t first. Then evaluate this integral. Multiply that 1 by s and finally replace s by s plus 3. That is effect of this change of scale. Okay. So 1 by s into integral s to infinity, that is effect of by t. Then sine t, Laplace transform of sine t is 1 by s square plus 1. 1 by s square plus 1. Integral s to infinity, so integration is with respect to s, so ds. Now 1 by s square plus 1, its integral is tan inverse. So tan inverse s, limit varies from s to infinity. As in the previous problem, tan inverse infinity is pi by 2. So we got pi by 2 minus tan inverse s. Then pi by 2 minus tan inverse leads to cot inverse. So 1 by s into cot inverse s. Now all the interior operations are over. The last operation is s is replaced by s plus 3. So 1 by s plus 3 into cot inverse s plus 3. Cot inverse s plus 3 by s plus 3. So there is a chain of operations may happen in the Laplace transform. So we think about the easiest operation will be in the outside. Whenever there is a multiplication by e raised to minus at or e raised to minus pt, that is simply a shifting in Laplace transformed domain. So that should be kept as the last operation. And we do the remaining operations in the same order. Without much difficulty, we can find Laplace transform. So that is all about the basic results related to Laplace transform. Now we are going to discuss what is inverse Laplace transform and also some basic properties of inverse Laplace transform. So the inverse Laplace transform is defined like this. If L of f of t is equal to f bar of s, then we put this L to the right side. So it becomes L inverse. So L inverse of f bar of s is nothing but f of t. Mathematically, L inverse of f bar of s is equal to f of t. This is simply the return journey from transform domain to time domain. L inverse of our transform domain leads to the time domain. So we have to recollect all the previous formula. For example, L of sine at, we know that L of sine at is equal to a by s square plus a square. That is, we are in the transform domain. Now we put this L to the right side, that becomes L inverse. So L inverse of a by s square plus a square is equal to sine at. We take this L to the right side, so L inverse of a by s square plus a square is sine at. That's the result. So now onwards, whenever we have seen something in terms of s, we are going to take back it into the time domain using our basic result. The first result, we know that L of 1 is 1 by s. So L inverse of 1 by s is 1. Then L of e raised to at is 1 by s minus a. So L inverse of 1 by s minus a is equal to e raised to at. Whenever you see 1 by s minus a, then automatically you think that its inverse is e raised to a into t. Then L inverse of 1 by s raised to n plus 1 is equal to s power gives Laplace transform of t raised to n. So t raised to n by n factorial. Next result is L inverse of 1 by, in the place of s I have s minus a. S is changed to s minus a whenever there is a multiplication by e raised to. So it is s minus a. So e raised to at into. So the effect of a is disappeared. So 1 by s raised to n plus 1. 1 by s raised to n plus 1 leads to the inverse t raised to n by n factorial, like that. Next result is L inverse of 1 by s square plus a square, that is equal to 1 by a sine at. We are familiar with Laplace transform of sine at, that is a by s square plus a square. In many cases, a need not be in the numerator. Actually, suppose here we have a, we can take this a to the left side. So L inverse of a by a square plus a square equal to sin at. The same result can be reformulated in a different style. Next is L inverse of s by a square plus a square is equal to cos at. L inverse of 1 by a square plus a square is equal to, instead of this plus I have negative. It happens only when sine function changes to hyperbolic sign. Next is about cos h. L inverse of s by, instead of plus in the denominator, minus L inverse of s by a square minus a square is cos h at. Next is L inverse of s minus b by s minus b the whole square plus a square. In the place of s I have s minus b in the numerator and denominator. This shifting is happened whenever there is a multiplication by e raised to. So I take this b, e raised to bt. So b will be disappeared. So s by a square plus a square. S by a square plus a square is cos at, like that. So we have to reverse all the formula to find out L inverse. So we have to write the inverse of all the standard formulas that we have learned in the first session. Now, next result is L inverse of 1 by s minus b the whole square plus a square. In the place of s, we have s minus b. That happens only when multiplication by e raised to. So e raised to bt. So this b is disappeared. 1 by s square plus a square is 1 by a sin at. So next result. Similarly for sin h. Then this is a property. Laplace transform of integral. When we take this L inverse to the right side, L of integral becomes division by s. So L inverse of division by s leads to integral f of tau d tau. Then L inverse of f bar dash of s. L inverse of some derivative leads to minus t into f of t. We are familiar with this result. L of t into f of t. L of t into f of t is equal to minus d by ds. This minus should be here. I make a rearrangement. So L inverse of derivative of transform leads to minus t into f of t. These results are very important in the problem solving sessions. Now, how to find inverse Laplace transform? There are various methods to find inverse Laplace transform. The basic and most simple way is using direct results. And second one is method of partial fraction. Instead of very complicated expressions in s, we write it in the form of simple fractions. Then we can find out L inverse using the standard results. That is second approach. And third approach is using properties of Laplace transform. For example, L inverse of t into f of t. L inverse of f bar dash of s. Derivative of L inverse. Sorry, L inverse of derivative. That leads to minus t into f of t, like that. And last method is called the method of convolution. That is a very important operation in engineering area. How to take convolution of two functions. And this convolution leads to inverse Laplace transform. As a first step, we are going to do some problems related to direct methods. Here we try to associate given function in S into a Laplace transform basic function. We have already familiar with the Laplace transform sin at, cos at, etc. We have given an expression in S. We try to connect it into our previous results. Okay. As a first problem, we are trying to find out inverse Laplace transform of s plus 3 by s square plus 9. All these expressions are in terms of s, so we are in the transformed domain or s plane. Now we have to come back from s plane to time domain. That is why we are applying L inverse. Now, as a first look, the numerator contains two terms s and plus 3. We can apply term by term division. So s by s square plus 9 plus 3 by s square plus 9. We are familiar with the term s by s square plus 9. This transform of a function, familiar trigonometric function. Then 3 divided by s square plus 3 square. This also transform of a familiar function. We make use of these concepts to find the inverse Laplace transform of this expression. We need to find L inverse, so we put the symbol L inverse on the left side. Then we can split it into two parts, s by s square plus 9 plus 3 by s square plus 9. And also L inverse is linear. We can calculate L inverse of first expression s by s square plus 9 plus L inverse of second expression 3 by s square plus 9. And this is nothing but cos 3t. L inverse of s by s square plus 9 is cos 3t plus this is L inverse of 3 by s square plus 3 square, that is sin 3t. So we can directly calculate L inverse of s plus 3 by s square plus 9 by observation and direct use of results. But unfortunately, direct application of result is very rare in inverse Laplace transform problem. But occasionally some simple problems may occur. Another problem, find the inverse transform of here Laplace transform of 3s minus 137 by s square plus 2s plus 401. Here also we try to express is the form of s square plus a square like that, because there are two terms. One term contain s, another does not contain s. So our aim is to express it the form of two fractions, some 3s by one expression minus another term, constant term by another expression. But here we don't get s square plus a square expression because it is of the form s square plus 2s plus 401. And in a very close examination we can see that we can create a square term involving s from here. Suppose s square plus 2s plus 1, we take 1 to here. So s square plus 2s plus 1 is s plus 1 whole square. Then we can take the remaining term here. Okay, we try it. Actually, I write the denominator first. 3s minus 137 by, I complete the square. I take half of the coefficient of s. Half of the coefficient of s is 2 by 2, 1. And add and subtract square of that term. Half of 2 is 1. Take the square 1. Add and subtract. When I add here, I got s square plus 2s plus 1. That is s plus 1 whole square. When you subtract it, we got 401 minus 1. That is 400. The denominator in terms of s plus 1. So we have to make the numerator in terms of s plus 1. Then only we can apply shifting theorem. So s plus 1 square plus 400. So instead of this s, I take s plus 1. So 3s plus 3. Here we have 137. To balance it, you have to write minus 140. We look back. Minus 140 plus 3. Minus 137. Okay, we got the correct thing. So why we take like this? Because the denominator is not in form of s square. It is of the form s plus 1 whole square. So we have to apply some shifting property. For that, whenever there is an s, that s should be replaced by some s plus 1. That is why we make this rearrangement. Then term by term division. 3 into 3 is a constant. S plus 1 by s plus 1 whole square plus 20 square. This minus 140 is a constant. Take it outside. 1 by s plus 1 whole square plus 20 square. Now everything is okay. We apply L inverse. L inverse of the left side is equal to, take these 3 outside because of the linearity property. L inverse of s plus 1 by s plus 1 whole square plus 20 square minus 140 into L inverse of this expression. 1 by s plus 1 whole square plus 20 square. Now this is s plus 1, s plus 1. This plus 1 is because of the shifting. That is multiplication by e raised to minus t, because the plus. So 3 is here, e raised to minus t. When I take e raised to minus t, we eliminate 1 from the scene. That is s by s square plus 20 square. S divided by s square plus 20 square. That is cos form. Cos of a is here, cos 20t minus. I take 140 here. Then 1 by s square plus a square is 1 by a sin 80. So 1 by a is here 20. 1 by 20 into. Here also shifting happens. So e raised to minus of this expression. E raised to minus t into sin 20t. Once again I repeat this. Here we have s plus 1, s plus 1 square. S is replaced by s minus a only when multiplication by e raised to t happens. So there is a multiplication by t is possible here. I take e raised to at. Here a is minus 1, s minus a form. So I take minus of this, e raised to minus t. And then s by s square plus a square. S by s square plus a square is cos 80. In the place of a we have 20. We do the same thing here. So we can take e raised to minus t common and simplify 120 by 20 is 7. E raised to minus t into 3 cos 20t minus 7 sin 20t. The second method is method of partial fraction. This method is familiar to us. In the plus 2 classes we have done lot of problems in integration using partial fraction. We will do the same thing here to find L inverse. In this approach we divide the given proper fraction in S into partial fraction. We have given the function in transformed domain, we split it into proper fractions. Then apply basic results to and linearity property of the inverse Laplace transform. The first problem is L inverse of 1 by s plus 4 into s plus 16. This is a proper fraction because the power of s in the denominator is higher than power of s in the numerator. Numerator there is no s term, so s raised to 0, power is 0. Denominator contains s into s square, leading term is s square, power 2. So it is proper fraction. We will divide it into a by s plus 4 plus b by s plus 16. So 1 by s plus 4 into s plus 16 will return like this, a by s plus 4 plus b by s plus 16. Then we multiply both sides by the denominator of LHS. When we multiply LHS by s plus 4 into s plus 16, that numerator term and denominator term get cancelled, we got 1. When we multiply it to the right side, this s plus 4 get cancelled, s plus 16 associate with a. Similarly, s plus 4 associate with b. Now we are trying to find a and b. The trick is we eliminate one unknown at a time. Here in order to eliminate a from this scene, we put s is equal to minus 16. When we put s equal to minus 16, this term becomes 0. So b is equal to minus 16 plus 4, that is minus 12. Minus 12 b is equal to 1. So b is equal to minus 1 by 12. Now we are going to find b, find a. For that I put s equal to minus 4. So this term get cancelled. So minus 4 plus 16, again 12. 12a is equal to 1, or a is equal to 1 by 12. Now we put a is equal to 1 by 12 here, b is equal to minus 1 by 12 here. Both the terms we have 1 by 12. Take it outside. So here when we take 1 by 12 outside, a is positive. So here we have 1, and in the place of b we have minus. Then take L inverse on both sides. So 1 by 12 is taken outside. L inverse of the first term. So L inverse of 1 by s plus 4 because a is taken outside. Minus L inverse of 1 by s plus 16. We are familiar with 1 by s plus 4 term. 1 by s minus a, that is e raised to function. E raised to, we expect minus, here we have plus, so e raised to minus of 40. Minus, here again I expect 1 by s minus a form, I got plus, that is because e raised to minus 16t. So L inverse of this expression, this rational expression gives 1 by 12 into e raised to minus 40 into 40 minus e raised to minus 16t. One thing we have to keep in mind, the denominator should be factorized first, then write a by one simple fraction plus b by simple expression in s like that. Then solve a and b. So that is all about this inverse Laplace transform. So in this session we have discussed two important points. One is Laplace transform some special forms, that is product with the t and quotient with the t, and their problems. Then we have seen what is the meaning of inverse Laplace transform and various methods to find inverse Laplace transform. In this session we have discussed only two simple methods. One is direct method using our basic results. Second one is using the partial fraction. Partial fraction is a direct approach that we have familiar with problems in integration. We extend it into inverse Laplace transform. That's all. Thank you very much. In the next session we will discuss the remaining topic related to inverse Laplace transform, that is some extension of this partial fraction method and also the convolution method. Convolution method is very important because in some problems it is very difficult to solve using our partial fraction approach. In that case, this convolution method is a direct method and it will solve all the complexities of solutions. Thank you.